Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on July 2nd, 2025, just yesterday. This paper introduces a method that dramatically speeds up autoregressive image generation, reducing over 1,000 generation steps down to just 48 for high-resolution images. The paper is titled Locality-aware Parallel Decoding for Efficient Autoregressive Image Generation, and it manages this speed up without sacrificing image quality. This is achieved through a new model architecture and a clever scheduling strategy that generates distant parts of the image in parallel. Also, the authors shared their implementation on GitHub, and it's a really complete package. You'll find the source code, pre-trained models, and all the scripts you need to run evaluation, or even train the models yourself. So you can definitely dig in and try this one out. Alright, so the first figure really drives home the performance claims. This plot compares different parallelized autoregressive models. Now, an autoregressive model is one that generates an image one piece at a time, sequentially. On the vertical axis, we have the Fréchet inception distance, or FID. This is a common metric where a lower score means higher image quality. And on the horizontal axis is latency, basically how long it takes to generate an image. So the sweet spot is the bottom left, fast and high quality. And you can see this paper's method, Locality-aware Parallel Decoding, or LPD, is right there, achieving at least 3.4 times lower latency than previous models, while maintaining or even improving image quality. So how did they achieve this speed up? Well, the core insight comes from looking at these visualizations. These are attention maps from an existing image generation model. An attention map basically shows us where the model is looking or focusing when it generates the next piece of an image. What you see, especially in those dark green diagonal lines, is strong spatial locality. This means the model mainly pays attention to nearby parts of the image. This observation is crucial because it suggests that distant parts of the image don't strongly depend on each other and can therefore be generated in parallel. Building on that idea of spatial locality, this next figure shows the core architectural change. On the left is the standard, slow method, raster order modeling. It generates one image patch, then the next, and the next in a fixed sequence. But on the right is the new approach, flexible, parallelized autoregressive modeling. It breaks this chain by using what are called position query tokens. These are essentially special instructions that tell the model to generate multiple distant patches all at the same time. This flexible architecture is what enables that massive parallel speedup. Okay, so with that flexible architecture, the next logical question is, what's the best order to generate these parallel patches? This figure compares different generation schedules. In the top row, you have the standard raster scan, just one line at a time. The middle rows show random and other scattered approaches, but look at the bottom row. This is the new locality-aware generation ordering. Notice how the new dark green patches are always close to existing light green ones, maximizing context, but they are also far from each other, minimizing interference. This smart scheduling is the second key ingredient to their success. This table then puts all those ideas to the test. It's a big system-level comparison against many other types of image generation models. Besides the Fréchet inception distance we talked about, it also uses inception score, which measures both image quality and diversity, with higher being better. Now, if you look at the bottom rows, you'll see this paper's locality-aware parallel decoding models. They achieve excellent quality scores, but they do it in just 20 steps, with latencies under half a second. This combination of top-tier quality and dramatic speedup is really the core result. So to wrap things up, this work really tackles the slowness of traditional step-by-step image generation head-on. By combining a flexible new architecture that allows for parallel generation with that very smart locality-aware scheduling system, the authors achieve a dramatic speedup. They reduce the number of generation steps by more than 12 times, from 256 down to just 20, all while maintaining top-tier image quality. It's a powerful combination of ideas that really pushes the boundaries of efficient visual generation. That's all for this edition of the AI Research Roundup. Thanks for tuning in.